I am Professor Antonio S. Marajas, and this is Computer Applications in Industry. So this is BCA 153, and our lesson is about relationship between digital logic circuits and your contact or coil logic. Now, we know that there are different types of logic gates, no? And this was already discussed to you during your subject BCA 1 to 2. Okay? So we know that there are different types of logic gates. We have the OR gate, the AND gate, the inverter, the NOR gate, the NAND gate, the exclusive OR gate, and the exclusive NOR gate. Okay? So what we have here is, for number one, for example, is an OR gate, no? A two-input OR gate. And we know that for an OR gate, just a review, we said that in an OR gate, if any of the input is high, then the output is high. Okay? So again, this is our symbol of an OR gate. We have two inputs represented by input 1 and input 2, and the output is represented by out 10. Okay? Now, the relay logic equivalent of your OR gate is this one here. And if you notice that the switches are connected in parallel form. Okay? Why? Because if you notice that if one of the switch here, for example, switch 1 is closed, then automatically your output 10 here will be energized, meaning to say 1. Okay? So, if this one here, switch 2 is closed again, and this one here is open, it will also energize. If both are closed, this will energize. But if both inputs are open, then your output is not energized, or the output is 0. Okay? So it's just like your OR gate. In other words, OR gate is represented by a parallel switch connection. And this one here is our Siemens equivalent. So we already discussed that when you have an open switch, it will be represented by an open contact. Okay? You will get an open switch, an open contact, and the output here represented by Q0.0, which is actually the equivalent of 10 in this particular relay logic. Okay? So, your inputs here in Siemens are represented by I0.1 and I0.2, representing SW1, SW2, or input 1, input 2. The output here, 10, 10. The output here in your Siemens is Q0.0. Okay? So that if this is closed, then Q0.0 is energized. Or if this is closed, then Q0.0 is energized. But if both are open, then Q0.0 is de-energized or not energized. For number 2, we have here an AND gate. Okay? So again, the AND gate is represented by inputs, input 1 and input 2, and output 10. Okay? For the relay logic equivalent, the AND gate is actually represented by a series connection of switches. So since you have two inputs here, you have also two switches here which are connected in series. Okay, again, output here is represented by 10. And what is the definition of our AND gate? It says, in an AND gate, all inputs must be high to get a high output. Okay? So if any of the input is low, then the output is also low. That is our AND gate. So in other words, if switch 1 here is open and this is closed, low or de-energized. If both inputs here, switch 1 and switch 2 are closed, then that's the time that your output 10 here is energized. No? So very much similar to that of your AND gate. That is why AND gate is represented by a series connection in our relay logic. Okay? Or switches equivalent. Now, what will be our Siemens equivalent in programming this particular AND gate? So you have two normally open contacts which are connected in series form, and the output again is represented by Q 0.0. So, since these are normally open, so your contacts here are normally open, and your first input contact, switch 1 here, is represented by I 0.1, and switch 2 represented by I 0.2, and the output again is represented by Q 0.0. That is the syntax on how to program our Siemens PLC. Okay, then we have here the third logic gate is the inverter. Now, for the inverter, you have one input and one output only. So, in the inverter, we define it as if the input is high, then the output is high. In other words, the output is always the complement of the input. So, this one here, the input again is represented by input 1, and the output is represented by out 10. So, how do we represent this in our relay logic? So, we have here switch 1, and this one here is our logic relay, okay, LR. Okay, and then we have here an LR again, which is normally close contact. This is the internal contact of your LR here, LR coil. The internal contact is LR, this one, which is normally closed. And then the output is represented by 10 here again. Okay, so that we said that if your input here in your inverter is 1, then the output here is 0. Okay, that is our inverter. So, let's try to find if it works here. So, if input is 1 here, that means that the switch here is closed. Then, your logic relay here is energized. If this is energized, then automatically your LR here will open. If this will open, then automatically your output 10 here will be de-energized. So, input is high, the output is low. Now, however, if let's say we go back to our normally closed contact, if switch here is open, basically, your LR here will not be energized. So, your LR internal contact here will just be closed so that the output here will be high. So your switch is open, but your output is energized. That is the representation of our inverter. Now, in the Siemens equivalent, we said that in our previous discussion, we said that one network or one rung should be represented by one output. Okay? In this case, this is equivalent to one network, and this is another network because it has two output. Now, even though LR here cannot be considered as an output, but since it is written in this manner, for now, we will just consider LR here as an output. Okay? So that we can represent here in our Siemens in this manner. You have network 1 because you have two outputs representation. So you have to have two networks. One output each network. So for network 1, you have an open contact, which is your switch 1. And then your output LR is represented by Q 0.0. And then go to network 2. Okay? Then normally close contact. Since your LR here is normally close contact. Okay? Then your output 10 is represented by Q 0.1. So if you notice that you have Q 0.0 here, your internal contact here is also Q 0.0. Okay? So what we have here is the NOR gate. Okay? So NOR gate, as we know, is just a combination of an OR gate with an inverter. Okay? So the NOR gate, here we have again two inputs. So we said that an OR gate can be represented by a two parallel switch. Then so you have here switch 1 and switch 2 here. Then the output here, instead of 10, you put here LR or coil relay or logic relay, LR. And then you place here your internal contact, LR, which is normally closed, then the output. Okay? So this part here is actually equivalent to your inverter. This one. Okay? So that is your inverter equivalent. So we just added the inverter in the circuit under your relay logic. Okay? So how do we represent the Siemens equivalent? So again, this one here, we have normally open contact, I0.1 and I0.2. The output LR can now be represented by Q0.0. That is for network 1. So because this one here is equivalent to one network. And the other network, which is this one here, is represented by this one, which is under network 2. Okay? So LR here can be represented again by Q0.0. We know that LR or Q0.0 here is our internal contact. And this one here, our final output 10 is represented by Q0.1. Okay? So I hope that you were able to get the principle on how the inverter is added towards your or to your gates, no? So next is your 2 input and on NAND gate. Okay? So again, NAND gate, as we know, is a combination of an AND gate and an inverter. So we have 2 inputs represented by input 1 and input 2. And then we have here the AND gate representation. This one here, which is connected in series. Okay? Now, instead of output 10, we represent it with logic relay again, LR. And then you have here the internal contact LR of your logic relay. And then you have here the final output represented by 10. Okay? So this one here, just like in your in our previous discussion in your NOR gate, this one here, this part here is your inverter. So this part here is also your inverter. Okay? Then we have here the Siemens equivalent. In the Siemens equivalent, again, switch 1 and switch 2 are represented by I0.1 and I0.2. And then the logic relay is represented by Q0.0. That is for network 1. For network 2, you have LR, which is represented by Q0.0, which is your internal contact. And the final output is represented by Q0.1, which is actually your 10, which is the output of your NAND gate.